let's just do a quick vote. If you have no idea, just go with your gut feeling, which one do you think it is? So this one, the way it's written right there, that left on boy, right on sled. So, okay, your answer. So we got 3. And right boy, left sled.
I agree with the other one.
Like the other one?
Yeah.
All right, and so the other ones we got 1, 2, 3, 4, 5, 6. So when we talk about relative motion, desired relative motion, if the sled were frictionless on top, sled, boy. If they were frictionless on top, which way is this going to move relative to the sled? If the sled's pulled that way,
It's just like stay still and the sled would just go under it?
it would. But so relative to the sled, which way is this going to go?
Nowhere.
Relative to the sled.
Oh, lead.
So relative to the ground, it's not going anywhere.
Yeah.
Relative to the sled, if it slides out from underneath it, from the sled's point of view, it's moving backwards. Moving to the back of the sled. That's what I mean by relative motion, desired relative motion. The boy that, if there were no friction there, the boy would slide to the back of the sled, and therefore, the friction acting on him opposes that. So friction's acting this way, so congratulations. Friction's acting this way on the boy, and this way on the sled. The other clue that the friction must be acting to the right on the boy is that if it is acting to the left, I have 3 forces. I have normal force, I have a weight, and then if I have friction acting back this way, then my net force would have to be that way. But acceleration is to the right. Force and acceleration, the total force and acceleration will always be in the same direction. That's the whole point of F equals ma. So there has to be something going to the right. And now friction between dad and ground.
Left on dad.
So dad, left on dad, and I guess right on ground. Alternatively, right on dad, left on ground. We were in that same situation again. Well, different, slightly different. Gut feeling, if you don't know, just go with your gut feeling. I guess Alan said first, left on dad, right on ground. Or do you want to make an argument for that? Nope, okay. Left on dad, right on ground. So I got 1, 2, I'm gonna assume you 3, 4.
No, actually, I'm voting for the other one now.
Oh. Right on dad, left on ground. So 1,
No.
2.
Wait.
Do you need a moment to think a little bit more?
Not on the first one.
So you're for, okay. So right on dad, left on ground. 1, 2, 3, 4, 5, 6.
Yes.
I think 7, 8. Somewhere around there. There seemed to be overwhelming support for this one instead of that one. Someone who voted whichever way, make your argument. Dominic?
Why, if the sled and the dad are both on the ground, I understand the dad's probably picking his legs up, are we assuming that he's just moving and sliding?
Yeah, I mean, he's stepping.
Yeah. So why would it be different from the sled if they're both touching the same ground?
Why would it be different?
Because the sled, it's left on the sled and then right on the ground.
Oh, so your argument, it would be the same direction.
I mean, if they're both moving to the right, why would it change?
It depends upon
It's the same.
the desired relative motion. Remind me, because I might forget in 2 minutes. I'll give you an example where they definitely would not do the same.
Okay.
All right,
Like-
tell me.
In this hypothetical scenario, like if there's snow on the ground, is he stepping? Would you argue that his foot is like backwards? Like, 'cause it's snow. I'm just saying, like, His foot would be sliding to the opposite, to the left, and backwards.
Therefore, friction would be acting to the right? Is that the argument you're making?
Yeah.
Yes.
And that's exactly it. Even though he is moving to the right. And so the people who generally vote for this, the argument is, well, he's moving to the right, friction's gonna be acting the opposite way. But it's really the foot. The foot is where the friction is taking place. His foot is acting to the left. That's why I drew it this way with the back foot down on the ground, because he's pushing. Now, walking gets a little bit complicated. So it is this one. So I have friction of dad, friction of dad. I'll get into the complications of walking in just a moment. Also the argument that if he's accelerating to the right, there's gotta be some force to the right. And none of the others are to the right. Now walking. And if any of you ever work for DuPont, do not do this. When I was working with DuPont, they had, the desk I had was wider than this. And there was a conversation on the other side of the partition that I wanted to take part in. And so I got up on the desk and I was leaning over to participate. And they stopped the conversation, told me to get down. They would not start the conversation up again until I actually got off the desk. They are very serious about safety.
And you're not.
What's that?
And you're not.
I thought that was a bit extreme, but it's hard to argue. The year that, one of the years I was working with DuPont, there were 12 injuries worldwide. The most serious injury was somebody stepped off a sidewalk and twisted an ankle. In the 6 months I worked with US Steel, there was one death, one arm that was crushed. I took a tour through, after I'd been at DuPont for years, I was working with US Steel, and I was walking through one of the warehouses, there was an open flame in one of the warehouses. And what was preventing, and the safety aspect was they had yellow tape on the ground that you weren't supposed to walk past, but there was so much filth everywhere that you had to be looking for the yellow tape. Or you could use common sense not to go near a flame, but. All right, so when you're walking, as I'm stepping like this, my back foot, I'm pushing with my back foot. When I land, the friction acting on my front foot still sort of wants to go that way, so the friction's acting this way on my front foot, but that way on my back foot. And it's still doing that until this foot comes off. I'm over this foot, so there's no friction at that point, and now I'm pushing with my back foot, so friction is now flipped the other direction. So between the feet, the friction will flip back and forth as one walks. Now, if you have not experienced it, and I don't recommend that you do, but at least you pull a lesson out of it. Walking on ice. If you've ever walked on ice, when your foot lands and then it slips out in front of you, it doesn't land and slip out behind you. Or the back foot slips. The example, there was one example where 2 feet on the ground friction's acting in opposite directions. The other one, I have a cart attached to we'll just say horse. Horse. As the horse is walking, the horse is pulling his feet backwards. I just simplify it. The horse, in order for the horse to accelerate to the right, his feet have to be pushing backwards. Argument that Sonny made earlier. So the friction acting on his feet is this way, the friction acting on the ground is back. But this wheel is gonna be rotating around like that as it moves this direction. In order for the wheel to move around like that, the friction acting on the wheel is acting this way, the friction on the ground is acting that way. Because if the surface were frictionless, that wheel would not spin at all. So relative to the ground, the wheel wants to do this, and so it's going to oppose that by applying the friction backwards on the wheel. Questions? This is a test level problem. Typically, the number of forces in a test level problem are anywhere from 28 to, I think 42 is the most I had. 28 to 42 forces. I don't know how many that is.
20 to 24 to 42 pairs.
No, not pairs. When you are done, if you count up the number of forces that are on the board, there should be an even number, unless there's an other. In the absence of questions, I've written up facades over there earlier. Let's actually go through a problem. And one that you will deal with again and again, box on ramp. So I've got ramp. We're gonna do a box on ramp problem from beginning to end. We're gonna start out with a frictionless ramp. This angle down here is theta. Those are the steps we're gonna go through. So force diagram, we've already done that today. Now the full force diagram would be including the ramp. Also, what we really care about ultimately is what is the acceleration of the box. So we really only care about the forces acting on the box, but just for now, I'm gonna go ahead and do both. Eventually, we'll just do the forces on the objects that matter. So I have weight acting down, I have weight acting up, I have normal force acting up to the right, I have normal force acting down to the left. And I'm gonna throw friction in here, and then we'll just set it equal to 0 in a moment. That's what we had before.
Wait, this is a frictionless ramp, so then would friction be?
Yeah, I'm gonna make it equal to 0 in just a moment. So that's the force diagram. Acceleration. Just based on your own personal experience, if I put the box on a ramp like that, which way would it accelerate if it's going to? That way? Stove?
Would it go down to the right a little bit?
Oh, yeah, definitely. When you say to the right, what you're saying is it's going that way, and I don't think that's gonna happen. That's not my experience that I put a box on the ramp and suddenly it goes shooting off. So it is going to go down the ramp. So the direction of acceleration, is going that way. Is there another question or comment that sort of got skirted over? Giovanni?
What earth are we on?
Pardon?
What earth are we on?
It actually does not affect what we're doing. It will only affect it when we get to the very end. But what earth do you want to make it Earth 2?
Let's go with 3.
What is the acceleration of gravity on Earth 3?
7.2.
Earth 2/3. All right, so we figure out just based on our own personal knowledge that it's going to accelerate down the ramp. Coordinate axes. If you want to simplify the math, strongly recommend one of your coordinate systems, one of your positive directions is the same as acceleration. Since acceleration is going down the ramp, I'm gonna set up a coordinate system, so one of them is down the ramp. And I'm just gonna call that I hat. J hat is gonna be perpendicular to that. It's a two-dimensional problem, so that means it's either gonna be pointing that way or that way, and it really doesn't matter which one you pick. If there's no preference, anyone with a preference, I guess I should start with, then I'm just gonna make J hat this way. So that's the coordinate axes. Now decomposition. So I have a coordinate system that's at an angle here. I look at the forces involved, and the question is, are any of these forces not completely in the positive or negative I hat direction or positive or negative J hat direction? Since weight is not in the I hat or J hat direction, it's an accommodation, weight needs to be broken up. So we need to break weight up. So I have a ramp like this. And that angle there is theta. Weight is acting down. If I am breaking weight up, whatever I'm breaking up is the hypotenuse of my triangle. I want one of my components to be in the I hat direction, positive or negative, and the other one along J hat. Well, I hat's down the ramp, so I'm gonna have one component this way and the other component that way, and that is a right angle. I've had some students draw this all the way down to there and here, making this the right angle, and that definitely will, that is more than quadrupling the amount of work you have to do. Unless you ignore some stuff. So if this angle here is theta, that's 90 degrees. One of these two angles is also theta. So first I'm going to look at this triangle here, the one with weight, the base, and here. So the triangle that I'm sort of marking the vertices with purple. If I look at that triangle, this is a right angle, that whole thing. And I know that, well, sum of an angles in a triangle,
180.
degrees. This is 90, so these two have to add up to 90 degrees. So this angle here would be the complement of theta. So I generally label that as theta prime. Let's see, theta prime plus theta is equal to 90 degrees. Or for those more sophisticated, pi over 2. So now I'm going to look at this triangle with the green parts. I know those have to add up to 180 degrees. That's 90 of it. So these two must add up to 90. So theta prime, if that's the angle is theta prime, this angle here must be theta. Now I'm looking at this right triangle here. My hypotenuse is the weight. This is opposite theta. So this is W sine of theta, because it's the side opposite my angle, and my adjacent side would be W cosine theta. Do a dramatic pause here. Is there a question?
The question would be, can you repeat all of that?
Well, assuming that something hasn't messed up with the recording, you can always watch there. All right. Let me go through, I'm going to go through a different way of doing it, just to see if the other way works better for you. And as far as redoing it, if this is similar to other Physics 151 classes, I will be asked the question several times throughout the semester.
Yeah.
And so it will definitely get repeated.
Okay.
The other way that you can do this, let's say that you are in a situation, your mind is blanking, because it's a high pressure situation. You don't solve the problem, the bomb's gonna go off. Now, when I draw my angles, they almost always look like 45-degree angles. It's really hard to tell. But let me just go to a more extreme. I got my level ground here, and I'm gonna draw something that's clearly under 45 degrees. My weight is acting down, and I'm breaking up into components. One component is in that direction, the other one is perpendicular to it. So I've got, well, one is gonna be in that direction, one is perpendicular to it, going through that point right there. So I've got that tiny little triangle right there. But clearly, looking at this, looking at my two angles, that's my right angle right there. This angle and this angle, one of them clearly is very much smaller than the other. Well, if this is a tiny angle, the tiny angle must be the same here. Or if I drew the big one, much steeper one, that angle there is theta. Weight goes straight down. Marginally better. I'm going to break it up into components. So one component is going to be perpendicular to the ramp, going through that. So I have my two components like that. This angle, I think, is clearly skinnier than that angle.
Yeah.
So this is the fatter angle. This angle is above 45 degrees. That's above 45 degrees. So those two angles would need to be the same.
Okay.
If instead of doing that way, the other way of looking at it is if you recognize one of them is going to be W sine theta, the other is W cosine theta. If you can try to draw it more realistically than everything being a 45-degree angle, you can just do sine of the angle, cosine of the angle, and then assign the larger one to the larger side and the smaller one to the smaller side. All right, another dramatic pause for questions.